as our speaker, and also two of his colleagues on a recent paper that's in press. Jeff is a professor of biostatistics at the Yale School of Public Health, and he's also a professor of ecology and evolutionary biology at Yale. Jeff received his PhD in organismic and evolutionary biology at Harvard, and then went on to be a Miller Fellow at UC Berkeley. And that's where I was fortunate to interact with Jeff. I was actually a postdoc up at UC Davis, but living in Berkeley. And we had a lot of opportunities to interact. And I feel like I've always been trying to catch up to Jeff. He was, so far ahead of me at that time in terms of the methods he was using compared to what I was doing. And I feel like I'm just always trying to catch up and keep up with him. Jeff works on a variety of topics relevant to evolutionary medicine. That includes cancer and evolution, disease transmission, antibiotic resistance. I mean, he's really an evolutionary biologist who's been able to move, that toolkit, those perspectives incredibly effectively into public health, and thus really is a great example of evolutionary medicine research as an investigator. He's long been on our invite list. I'm really glad we could fit him in, and we invited him to talk about any topic. It was an unusual kind of invitation because it's like, if you want to talk about the cancer work you've done and phylogenetics and cancer, that'd be great. Or it could be about disease transmission. He chose to focus on recent work that he's done as you all know, on the durability of immunity against reinfection by SARS-CoV-2. Looks like really interesting work. And he also invited two of his collaborators on this to join, which we're really excited about because we love that format at Club EvMed. One of those collaborators is Alex Dornburg. He's an assistant professor of bioinformatics and genomics at University of North Carolina at Charlotte. He was here in the Triangle for a while and even a recipient of a TriSem grant. So we're always happy to feature our previous recipients of grants. He's an evolutionary biologist. And he has very broad interest in vertebrate evolution, especially in terms of fish, and has worked with a variety of people who are heavily involved in TriSem. And then we also have with us today Hayley Hassler. She's a research associate in biostatistics at Yale in the School of Public Health, working with Jeff. And Hayley received her undergraduate degree and master's degree at Clemson. And so we're really happy to have you guys here today. Thanks so much for joining us and sharing your work. And I'll turn it over to you. Thanks.
Okay, great. Thank you for that gracious introduction, Charlie. Let me just start the screen share. Can you just confirm that everyone's seeing the intro slide fully correctly? Great. As Charlie mentioned, I've got two of my co-authors here right now, Hayley Hassler and Alex Dornburg. This right here you can see is the full co-author list for this topic, the durability of immunity following infection by SARS-CoV-2. This is work that is complete. It's going to be coming out in publication form at the very beginning of October, and I'm really glad to have the opportunity to present it now. And we've got some follow-ups we're working on too, so that's exciting. So in terms of the contributions, so this is work that Alex and I basically put together as part of a NSF Rapid grant. It's of course one of these things where we wrote a grant to do one thing. This is what we ended up doing, and we're still trying to get that first thing done. But this one's come out, and it's probably more important than what we proposed to do anyway. So this is really a very exciting project. Hayley Hassler, I had sort of like met and we figured out, oh, maybe we had some mutual interests, and I got her employed to work with me, and this ended up being the major project that she worked on, and we could never have done it without her. She's been a phenomenal resource for getting the actual hands-on stuff done, because Alex and I have not been able to do that, and she's so efficient and does it very well. We also had contributions from Javier Singh doing just a bit of literature work, from Sayaka Mura and Sudhir Kumar, just contributing some other phylogenetic methods for a few small pieces of this work, from Zheng Wang, who's in my group, who helped gather some of the initial data sets of all the SARS-CoV-2 sequences, Nancy Ruddle, who taught Alex and I our immunology so we could actually do this project, and Alison Galvani, who helped edit the final paper, and that's kind of it. Alex and I have worked together for a long time on a lot of projects, He's one of my best collaborators. We just have this really productive thing going, and it's really enjoyable. All right, so, and they may interrupt me at any time if I start saying things incorrectly, which I do. So, here we go. Let me tell you what we did. If I can just get, there we go. Probably all of you know the durability of immunity on natural infection has been called one of the greatest unknown factors of the COVID-19 epidemic. There have been papers that have come out. These are a little bit older, but there have been ones since then, and the story hasn't really changed. Big questions for COVID-19. This is one article, Nature video. What are the big questions 6 months on? One of them is, what's the durability of immunity once you get naturally infected? This is from the news site Stat. 7 months later, what we know about COVID-19 and the pressing questions that remain. Pressing question that remains, what's the durability of immunity if you get infected? Now, there have been a bunch of papers that have come out that sort of like seem to speak to this question. You probably hear, every time one of these papers comes out, it gets on the news. And then it's sort of a disappointing result, because essentially what they say is, oh, well, we followed antibodies, basically responses. And yeah, the antibodies are still there at 6 months. They're still there at 7 months. They're starting to decline. And it's sort of like, well, okay, but what does that actually mean for me? Am I going to get infected or not? And they don't answer that question because we don't know what level of antibody in SARS-CoV-2 allows infection. And in order to get that information for SARS-CoV-2 using the traditional approaches that people have used, we need many, many years of data, because we need to actually see people get reinfected and see what antibody levels they have. And that's not something that we're going to get anytime soon. So the question is there some way we could kind of address this, this question? And it's an important question because it's the news of like antibody levels lasting shorter or longer has like sparked fears. So fears that immunity to COVID wanes fast, but the antibodies alone don't really convey the durability of immunity. I mean, the fact that they're declining doesn't say that you can't avoid being infected. Other studies, instead of saying that it fades fast, some have questioned whether it's even possible to get COVID-19 twice. Now we have empirical data that shows that you can, but it's been debated, and the question is like, how much immunity do you have if you were infected once with COVID-19? And what I want to argue is that it's not either of those questions. We actually do have the information to answer this question. And that's because, on the contrary, we actually know something about the durability of immunity to SARS-CoV-2. And that something comes from the fact that it's an organism and it's diverged from other organisms. And in a world of evolution, things don't diverge all that fast. And in fact, there's quite a few coronaviruses that aren't all that divergent from SARS-CoV-2. So we can gather phylogenetic information on those organisms and get a better idea of what SARS-CoV-2 is likely to be like. So these are just showing you here the molecular divergences in the blue. That's the percent divergences of SARS-CoV-2, SARS-CoV-1, HKU1, NL63, MERS, OC43, and this is 229E here, HCOV229E. So these are MERS, SARS-CoV-1, and SARS-CoV-2 are the three zoonotic coronaviruses. MERS and SARS-CoV-1 never went pandemic, but SARS-CoV-2 did. And then the three HCOVs, HKU1, NL63, OC43, and including HCOV229E here, 4 HCOVs, are human coronaviruses that endemically spread in humans. We've probably all been sick from infections from those human coronaviruses. They aren't something that is a lot of medical attention has been paid to, because people don't find them all that debilitating when they get them. And the remarkable thing about SARS-CoV-2 is that unlike those, it can kill you, maybe because we've never been exposed to it previously, because it's somewhat diverged from the others. Because they're relatively closely related, we can actually understand their phylogeny, and we can understand what their phenotypic traits are like compared to other human coronaviruses. So what I want to argue is that we can use these genes of the coronaviruses to actually understand something about their relationships. And just to show you one piece of evidence that there is information here, if you do the plots of phylogenetic informativeness, which I'm very fond of, looking at the various genes of SARS-CoV-2, across multiple species. This is a phylogenetic conformance plot across many different isolates of SARS-CoV-1 and SARS-CoV-2, and some of the wild relatives of them, some of the SARS-like viruses that have been isolated from reservoir species. You can see that there's actually quite a lot of phylogenetic information in the spike gene, S here, which is in purple, and in some of the other genes as well, telling you something about the phylogenetic relationships of those. And not just their phylogenetic relationships. When there's information in the genes, that implies that there's information in the sort of organismal properties or phenotypes as well. Okay, so what we did was we constructed a very large phylogenetic tree with a lot of different SARS-CoV-2, SARS-CoV-1, and HCOV isolates. And the idea was just to make sure we had a very strong phylogenetic tree. We did extensive sampling of the species. And what you can see is that here, and the scale, well, the important point is that the nodes are indicated for their degree of support, and the cool colors like blue indicate very strong support, red colors or orange colors indicate low levels of support. So there's a tremendous support to the backbone of the phylogeny of all of these organisms, and that backbone is actually all we're really concerned with, because after we made this tree, what we did essentially was prune it down to those organisms that we're actually going to be able to trace phylogenetic relationships among the phenotypes we're interested in, which are all human-infecting phenotypes. So this is the phylogeny that we then used of SARS-CoV-2, SARS-CoV-1. You can see MERS is an outgroup to the 2 SARS-CoVs, and then you've got the 4 human coronaviruses, which appear in 2 sister clades, outgroups to the zoonotic coronaviruses. And we have 100% bootstrap support on this tree using multiple methods, et cetera. So very, very well-resolved tree. The phylogeny can be easily used for this purpose. All right, so what can we actually get out of understanding the relationship between these human coronaviruses and the zoonotic coronaviruses? The main thing that's incredibly useful is that longitudinal data has been collected on human coronaviruses, which tell us what antibody levels individuals had. These are just 11 different individuals in this particular data set by Edridge et al., where they actually looked at individuals and said, oh, well, what was their antibody level? What was their antibody level? Every 3 or 6 months, they would chart their antibody level. And then they would also note times when there was an increase and there was an infection that happened. And that gives this really advantageous data set that not only tells you how long it takes for the antibody to wane, but also what the relative probability of an infection occurring at different levels of waning is. So what we did was take this data that was just gathered empirically by Edridge et al. In this case for NL63, 229E, and OC43, because unfortunately the sample size for HKU1, the 4th coronavirus, human coronavirus, was too small for an analysis to work on it. But for these 3, there was plenty of data. And what we did was take that data to try to understand what these probabilities of infection given antibody level were and what the waning levels of antibodies were as well. So how do we do that? Well, here's a typical anti-N IgG waning antibody profile over time from that study. This is for HCOV-229E. And what we're able to do is actually look at what the peak normalized antibodies levels are. What that means is antibody levels, when you get infected, they go up and then they start dropping. So we inferred what the peak was. You can see the peaks right here. And then looked at what the rate of antibody decline was after that. And we used multiple instances of this and just came up with essentially a typical waning profile for antibodies for each of these individual viruses. Once we figured out the typical waning profile, then we could figure out what the daily probability of infection was given that antibody level. Again, looking at the exact level of the antibody prior to an actual infection occurring. And every time we could look at that, we could look at, well, there was many instances of not being infected until you were down here, and then you got infected here. And you can basically just do a logistic regression saying what's the probability of infection on a given day is what we actually use down at the units of days, given the antibody level. All right. And so that gives you a curve that looks like this. You can see at the very high levels of antibody, you have very low chance of getting infected, but then it starts rocketing up a lot faster as you get to much lower normalized antibody levels. Then we can actually calculate the probability of reinfection over time looking across days, because we know the antibody levels typically, typical antibody waning profile, and we know the probabilities for each antibody level. And that gives us this probability over time. Every day here gives us a certain probability of getting infected. The reason it declines later is because you're likely to get infected by then, and we're only looking at one instance of infection. You know, if you're infected here, then you're not going to be infected later, at least the way we're calculating it. So the point is, when would the first reinfection occur, not the second or third or something like that. Then we can do that for all three of these. So here's HCOV OC43, NL63, 229E. You can see that they're, you know, fairly similar, slightly different perhaps. Oh, and one thing I failed to mention is we have a couple different curves here. And that's, I'm not going to go through all of the different ways that we did it, but you can see down here, there's a lot of different data sets based on anti-N IgG. In other words, if you use the nucleocapsid IgG antibody data, or anti-S data, if you use the spike gene IgG data, and then there's also just whole virus lysate data. So we basically analyzed all of these data sets, use every which way that we could, given the data that was available, and all of those curves are shown here. And they're largely overlapping for most of these, except for one instance, which I'll tell you about. And so the point is, we can get these antibody levels, their probabilities of infection, they're consistent across antibody levels, and they're also consistent across phylogenetic trees, which I'll mention more later if I have a moment. And then these give us these probabilities of infection for each of these human coronaviruses over time. Now that's great. Everyone wants to know what their likelihood of being sick again is in another year. But what we really want to know about is SARS-CoV-2. And unfortunately, we don't have Edridge style data for SARS-CoV-2. We don't have, you know, 10 years of data on individuals, or 20, actually, I think it's 30 years of data, almost 30 years of data from the Edridge study. So we can't do that for SARS-CoV-2, but what can we do? Well, what we can do is use the power of evolutionary biology, go back to this phylogenetic tree, and if we know the properties for these species, then maybe we can figure out the properties for these species, including what information we do currently know about them, which is about their antibody waning. So if we can use the probability of infection given antibody levels data from the human coronaviruses, a little bit of the waning data from these species to the extent that we know it, especially SARS-CoV-2, where we know very little of the waning data, then we can like augment that waning data for SARS-CoV-2 based on ancestral and descendant states estimates, and also estimate the probability of infection given antibody level via ancestral and descendant states estimates, giving us an estimate for the time to reinfection for SARS-CoV-2. That's the whole plan here. So again, here are the three human coronaviruses. They're at the bottom of the chart and they're related like this. And then we're going to go up and we're going to compare those to the zoonotic coronaviruses. And use, as I mentioned just a slide ago, the data on the waning of antibodies in response to infection from those, so that we can understand, so we can use whatever empirical data we can get in addition to the tree, which is important because the phylogenetic information only goes so far. And these are just two plots of example data sets for what we had to draw things from. You know, everything comes in different formats, and you usually have to just extract it from the figures, because in the immunology, it's not the same as in evolutionary biology. They don't usually include all of the data on GenBank or whatever. So you just have to like mine it out wherever you can get it. All right, so here's the point. We used this continuous ancestral and descendant state inference. We used a Brownian motion model of trait evolution to provide the long-term estimates of the extended estimates of the waning of immunity. In other words, to understand better what was happening farther along on the waning side for the MERS, SARS, and SARS-CoV-2 waning antibody profiles, the probability of infection over time, and the probability density of reinfection. And just to cut to the chase, our main analysis yields a median time to reinfection for SARS-CoV-2 of 1 year and 7 months. For SARS-CoV-1, it's quite a bit longer. For MERS, it's quite a bit shorter. And for the three human coronaviruses, it ranges between basically 4 to 6 years. And oops, sorry, my slides are advancing of their own accord. Here we go. So just to show you, we studied a number of different data sets. Depending upon the virus, you could get different sets of data. And then here are the estimates that we get for all of those. You'll notice that SARS-CoV-2 is actually quite consistent. Most of the inconsistency comes in MERS, which has two data sets which seem to have very different antibody waning profiles. And we don't have any idea which one is right or correct, but there's just a discrepancy in the literature there. But the rest of it, the analyses were fairly consistent across whatever we could throw at it. Changes in the tree, changes in whether genes were recombining or recombining, what inference method we used, et cetera, et cetera. So a lot of robustness to the data. And here are the probabilities of reinfection just shown graphically. Probabilities of no reinfection. So how long can you go basically and not expect reinfection for each of these viruses? For SARS-CoV-2, again, any chance, maybe you could go, maybe at best, around 10 years or something and possibly not get reinfected, but most of the time, within a couple years, you're likely to get reinfected just based on natural infection alone under endemic circumstances, which I'll talk about in just a moment. And additionally, we can look at the other ones. You can see there's some variation in the probability of no reinfection for SARS-CoV-1 and MERS, very consistent results for OC43 and L63 and 229E. Okay, bottom line is it makes sense, just to interpret this a little bit, I think it makes sense to get vaccinated, right? Because you want to stay up here on the probability of no reinfection having recent exposure rather than farther along where you're likely to get reinfected over time. So what are the main conclusions of the result? This ancestral and descendant states estimate of the timing of the waning of immunity can facilitate quantitative analyses for all the policy decision-making that we're doing with regard to individuals who've recovered from COVID-19 and may be viewed in some parts as immune to reinfection. This durability of immunity has implications for the deployment of recovered healthcare workers, for travel restrictions, for decisions regarding how students obtain their education, for prospective vaccination protocols for clinical trials, as well as for the opening and closing of economic sectors in response to predictive models of the epidemic. It's very hard when you don't have any idea of what the immunity is to make these SIR models mean very much because you can't predict more than a couple months into the future. And our estimate argues strongly against any claim that there's some long-standing resolution that could happen due to herd immunity from natural infection. Such a strategy jeopardizes millions of lives, entailing high rates of infection, morbidity, and death every 1.5 years or so. So it provides, I don't mean cyclically, I just mean over 1.5 years, you get back to a point where you're going to be not immune anymore. This provides some guidance as to the likely timescale of immunity conferred by a typical vaccine, just on the very vague analogy that vaccines and natural exposure are somewhat similar. And the approach has general applicability to rapid prediction of parameters of novel pathogens, provided they're embedded in a clade containing 3 or more previously studied human pathogens. So anytime we have these sort of human pathogens in a clade, and they often are in a clade because of course they have inherited characteristics that allow them to become human pathogens. Most pathogens have relatives that are also pathogens. We could apply the similar approach, and it gives us a whole set of tools for understanding some of these things that usually take a long time to understand very early in pandemic spread. So Alex and I are very interested in developing these tools further to have sort of a tool set in place for the next pandemic. I have one more slide, which is our caveats. I just want to point out that the research addressed the durability of immunity in response to typical natural infections under endemic conditions. That is, all that human coronavirus data of the antibody levels, et cetera, was taken from endemic transmission, not pandemic transmission. That means it's just circulating around. It's been around for a long time. And everyone's sort of basically been exposed to those viruses once before, which is not what's happening in the pandemic. What that means is we need to be a little cautious about saying this is the probability of reinfection during a pandemic. There's sort of two push me, pull yous, and I'm not going to try to resolve it right now. One is, of course, during a pandemic, most people do not have good levels of immunity. We have naive immune systems. That makes us much more susceptible. That means in general, the probability of reinfection is going to be a lot shorter. On the other hand, during a pandemic, we're doing all of these interventions to stop people from getting infected that normally don't happen at all for human coronaviruses circulating. So both of these factors are at play, and they vary over time. And so it's pretty complicated to make an exact prediction of the reinfection time, but this can give you an idea of what the general picture is even for the pandemic. Like, what kind of duration do I have some reasonable level of immunity for, and when does it fade away? Next, our estimate and its uncertainty should be understood as a prediction of the average durability, not some universal durability for everyone. Baseline durability is used in our inference were average times of waning among multiple infected individuals. Any one individual could have longer or shorter durations of immunity, depending on their immune status, their cross immunity, their age, other factors that you've probably all heard about that relate to whether or not you're likely to get infected and likely to get sick with SARS-CoV-2. And lastly, because SARS-CoV-2 is a novel virus to the human immune system, I've been talking about reinfections, but I do just want to mention that reinfections may not exhibit the same severity as first infections. And that's all I have to say for caveats, and I'd be pleased to open the floor for questions from anyone. Again, Alex and I sort of had a lot of fun putting this together, this project, and Hayley is sort of the master of actually doing most of the technical work to get the answers done. And so all three of us would be delighted to answer questions as we move forward.
Okay, thank you very much, Jeff. That was fantastic. Thanks for sharing that. Really fascinating results. I can't wait to see the paper. Once it's published, we're going to share it with everybody. It's not available quite yet. We have some questions, some people with hands raised. We have some questions in the chat. I've got about 4 or 5 questions myself, which maybe I'll get to. I want to turn things first to Katya. Katya Cole, please go ahead and ask your question. Great to see you.
Hi there. That was a fantastic talk. I really enjoyed it. I also have about 4 or 5 questions, but if I can just ask 2 quickly for now. One, and I think it reflects another question in the chat maybe. It seems like kind of the hazard of infection, as a function of kind of your antibody levels depends in part on how much circulation there is, right? So I didn't see any kind of R0 or kind of force of infection or anything like that kind of come into play in terms of your analysis. So I was wondering kind of, where is it hidden basically? And yes. Then, yeah, go ahead.
Sure, I'll answer that in an ask another one. So it's all hidden in that human endemic, in that distinction I made between pandemic and endemic circulation. So the endemic coronaviruses are assumed to be circulating at a certain level. And so where it's hidden is in the fact that we're basically assuming that during endemicity of SARS-CoV-2, not exactly assuming, right? Because we have the whole phylogenetic analysis and the correlations, et cetera, but we're kind of assuming, or we're analyzing on an evolutionary sense, SARS-CoV-2 and believing that it has some evolutionary relationship to those, and therefore because of that evolutionary relationship, it's going to have the same kind of circulating level as those other coronaviruses. Now that's not accurate, right? It's going to be different in some way, but I think there's some reasonable sense that it's probably going to be similar, right? And that it's a very complex function, as you well know with the work that you do, but it's very complex how that all operates, and we're not going to be able to illuminate anything about how it operates from this kind of analysis. But I do believe that despite all that complexity, it's one of these sort of like levels of analyses things that we're able to say something about the wider level of what this means without actually knowing really what the circulation of SARS-CoV-2 will be at another time. Yeah. One other point that I'll just mention, it's not directly related to your question, but I think is an important point, probably someone's going to ask this question if I don't answer it, is just that, one of the things that we've noticed is that, of course, organisms evolve over time, right? So, but that organismal evolution is happening in the human coronaviruses as well, and was happening during their endemic circulation. And so we're averaging over that. So the way to think about this is that we're basically taking an average over an average over an average over an average, right? There's a ton of complexity that we're not taking into account or not thinking about. We're just averaging over all of it by using endemic circulating coronaviruses as our baseline.
Great. And then the second question I had was actually kind of related to the virus evolution versus waning immunity, but you just answered it. So the other question was when you have these very disparate estimates for SARS-CoV-1 and SARS-CoV-2, in terms of the Brownian motion model that you have, et cetera. So is the reason why they're so different, is it just because their antibody levels decline at different rates? And you basically, the Brownian motion model is kind of that noise or kind of difference in terms of just the response to a specific or the risk of infection given an antibody level? Or what's the data that kind of makes those estimates between SARS-CoV-1 and CoV-2 so different?
So I'll give you one answer, and I'll invite my collaborators to answer that if they have a better, more refined answer than I have. I'm just going to tell you why it's difficult to say, and that's that we have 4 different parameters in that ancestral states evolution inference, right? Because there are two parameters for the logistic function for the probability of reinfection, and there's two parameters for the waning of the antibody, because it's an augmented exponential. So it's got an augment and then exponential decline. And so a lot of the harder early part of this work was sort of figuring out how we could do this, given that we couldn't have too many parameters and given that there's, what information that was there. Anyway, the bottom line is with 4 parameters and all of their correlations involved, it's a little tricky to sort of dig out exactly why things are happening. But I would just generally agree that the waning of the SARS-CoV-1 is different, and I think that that's playing into the rest of the analysis in a way that allows it to be pretty different. And I don't know if Alex or Hayley have any more to add to that.
There's one other point too, is that when we're generating these profiles initially for the other viruses, that studies have different cohorts, which also plays into what an initial waning is going to look like, whether you have a cohort that's had severe infection versus the SARS-CoV-2 data that we were using was basically a unbiased sampling of everyone in Iceland that they were monitoring, which was about 1,700 individuals. We have across the whole population. For MERS, we have 2 studies with very low sample sizes that were giving very different results. So that also accounts for some of that heterogeneity between the viruses. We basically just need more data to get a more refined profile.
Which we were actually quite worried about in doing the analysis until we realized that even though that was that heterogeneity, we still got the same results for SARS-CoV-2. So we felt much more confident that the results are sound.
Okay, great.
Yeah.
Great set of questions, great answers. Appreciate that. Joe, you had your hand up. Do you have a question?
Yes, I do. And again, I agree. Very, very nice analysis. I also had concerns about the different dynamics that would be occurring between an endemic and a pandemic state, particularly the possibility, and I know your model sort of assumes that the mutation rate is phylogenetically constrained, but it seems to me that in a condition of pandemic, there's more possibility for the evolution of hypermutator strains. And we have some evidence that this is happening with SARS-CoV-2, particularly with things like Delta having an R09 compared to the Alpha strain. So I'm wondering if you guys ran different mutation rates and then examined the duration of immunity.
We did not analyze mutation rate. In fact, there's no explicit mutation rate in the analysis. The only way that effectively comes into what we did is in the phylogenetic analysis. Of course, there's a substitution rate, and we did use the substitution rates both to make molecular evolutionary trees of each phylogeny of that group and to make time trees of every phylogeny for all of those organisms. So the only sort of robustness I can say to mutation rate that we have built into our analysis is that we did a lot of different tree building in this project. We built the trees 10,000 different ways. Hayley is responsible for actually running all these crazy number of analyses that Alex and I dreamed up. So we did evaluate very carefully whether using a molecular evolutionary tree or a time tree, or whether reconstructing the tree with RAxML or a bunch of different ways, tree time, all kinds of different programs. Whether any of these things made a difference, none of them effectively made a significant difference to the result. So I can none of that addresses your question, because your question is really about whether or not a differential evolutionary rate to SARS-CoV-2 might entail a different result. And all I can say is if there really is a different evolutionary rate because of the higher population size due to the pandemic, or because it evolves an ability to mutate at a faster rate, then that would tend toward even shorter durability of immunity, because that durability of immunity, as we've taken in, takes into account sort of evolution of the virus in the human coronaviruses, which have a certain evolved rate. The only thing I would say to push back just a little bit on that is that it's true that apparently quite to a lot of evolutionary biologists' surprise, the SARS-CoV-2 has continued to evolve a bit, like with the addition of Delta, et cetera. But one would think that at some point it's going to hit some sort of level where there's not really anywhere more virulent it can go. And it's not clear to me whether that jump up for Delta, what I often wonder about is what was the historical evolution for all of those other human coronaviruses when they came into humans? Did they have a bunch of jumps up like this? I don't know, and I can't really make a comparative statement or know that. But a really interesting question. I would love to know more about those zoonoses and what the consequences of them were. So, so not the most satisfying answer, but I hope I've at least provided some illumination to the topic. And I don't know if Alex or Hayley, you want to say more?
Yeah, Hayley or Alex, do you have any thoughts on this or other questions?
No, I was just going to say that also the genetic distance between the original SARS-CoV-2 and maybe the Delta variant is really small. So even if we added that into the analysis, I don't think it would make that big of a difference in our estimate.
One of the interesting things, sorry, I'm just going to add one more thing, which is, one of the interesting things about the coronavirus is that sort of no one really paid attention to too much, except for maybe coronavirus researchers, is that, they don't evolve at that fast a rate. Like you compare them to influenza, they're evolving at a much slower rate. And yet they still manage to somehow evade immunity with the tip of that, with that recombination binding domain of the spike protein. Somehow, like, it's very sensitive. So just a few variants can somehow change the surface of that and allow it to evade immunity. And I don't really know the detail of how that works, but I think it's a very fascinating case where where coronaviruses have evolved an ability to evade immunity that isn't as dependent on rapid mutation rate, because just changing a little bit seems to do a lot for them compared to flu, where it has to change a lot for it to do a lot. And it does change a lot, but it's just a totally different pace, and yet it still achieves some of the same goals over the same kind of timescales.
Yeah, it's interesting perspective. Thanks, Jeff. And Alex, did you have anything you wanted to add in there?
I was just looking through the chat. Somebody was asking about antiviral medicines. We haven't talked much about antiviral medicines, but I do think that there is sort of a way to start thinking about this in terms of vaccinations as well, but it gets a little bit more complicated when you start thinking about what the vaccine is targeting versus what the virus is doing, which we're averaging over when we're talking about endemic conditions. But yeah, in terms of the genetic distance too, just to circle back to that, the modulations that we're doing when we're doing the phylogenetic analysis of branch lengths vastly exceed those distances that we see with a jump from delta to alpha. So I do think that these analyses are pretty robust to changes in mutation rate, at least on the phylogenetic level.
Okay, great. Yes, and Alex, you were bringing up, I think, the question in the chat from Diane Sherry. Diana Sherry, she said her microphone isn't working. She had a question: what is your definition of reinfection? And then, yeah, does anyone have any thoughts about antivirals? So I don't know if anybody wants to address that question. What is reinfection? How's that defined exactly?
So let me just say that for our purposes, reinfection is defined on the basis of what this Edridge et al. Study said, where they looked for these big jumps in antibody level in response to presumed infection. Like, they don't actually know that the infection was happening. All they know is the antibody level jumped very strikingly. And I would just invite you to look at the Edridge et al. Study to sort of figure out how they decided on that. We use the same criterion that they used. And so we're basically saying, so reinfection doesn't necessarily entail any symptomaticity whatsoever. It just entails that you actually had an immune response to the virus.
Okay.
So that's an important thing to understand. It's a good question.
Yep, that is important. Okay, we have a question from Martin Bobrowski. Please go ahead, Martin.
In the various families of the coronaviruses, do they all share the same receptors? And if they have different receptors, is that in any way important, or does that wash out because of the way you're analyzing the data?
There is some similarity and some differences is the answer. I don't know, Alex, if you have more to say about it than that. There's some similarities and some differences. We didn't go into a lot of detail about that. I think what our baseline analysis was to say, oh, these are related viruses. They're going to have kind of similar ways of interacting with the immune system, regardless of what their necessarily receptor is, or any particular biology that they see. And so let's just analyze them all together on a phylogenetic scale and use as many parameters as we can throw in there to inform the inference. Yeah, and that's basically all I have to say about it. But I don't know if Alex or Hayley have more to say.
Yeah, and there is some cross-reactivity between exposure to something like HKU1 and SARS-CoV-2, et cetera. So they do seem to be fairly conservative with regard to the response that the human immune system has to them. So we're using that to justify this approach.
Yeah, that's in the Edridge data that we looked at. So you can actually see, like, when a big jump occurs in one human coronavirus, you can see a little jump in the antibody response to the other one, just because there's this cross-reactivity that means that the antibodies of one react to the sensor for the other, essentially. So so there's definitely a lot of cross-reactivity that, or not a lot, there's definitely cross-reactivity that implies that that the immune system is not very far different in its reaction to these different viruses.
Yeah, and I think that there actually have been several publications that have looked at the cross-reactivity with SARS-CoV-2 compared to some of the other seasonal coronaviruses.
Even one, I think, that was showing just empirically that if you recently had a human coronavirus cold, you were less likely to get infected.
Okay, thanks. We have a question from Michael Hochberg. Go ahead, Michael. Good to see you.
Yes. Right. Hello.
Hi, Michael.
This is really great work. I'm wondering what your work says for vaccination policy, and in particular, whether or not a strategy could be to bump up the immunity of waning immunity in those who have been infected.
It's a fabulous question. We are working on that, and we have some very preliminary results, which I'm probably not going to share in anything other than a very vague form at the moment. I guess what I'm happy to say is that we're working on it. It will hopefully come out very, very soon also. But the basic idea, of course, as you've said, is that maybe we can use this to project the waning based on vaccine exposure as well. And I'll just say that, like I said in my conclusions here, the preliminary data that we've been looking at seems to imply that things are not terribly different between vaccines and natural immunity. I don't think that's really a direct inference from our data, but that's the kind of result that we're getting, and generally accords with what has been popularly talked about with the different vaccines. So the more the vaccine protects you against immunity, the longer your duration is likely to be. That's hardly a stretch from what you might have already inferred from data that's out there. So overall, if you sort of apply what we've learned about natural immunity and just think about what we know about the vaccine-mediated immunity based on clinical trials and observational studies that have been done, nothing is inconsistent in what we've inferred so far in that preliminary work we've done.
Okay, great. We have a question from Terry Taylor. Go ahead, Terry.
Thank you very much for excellent presentation, a super project. I'm coming at this subject from the policy, health security policy direction. And so I'm really interested in understanding the graphs that you produce. They show a steady decline. Presumably this is about averaging out the data, because there would be, once perhaps in pandemic conditions, could be repeated infections, and maybe the antibody response varying with individuals would spike up again. So it would be the true graph, say, for an individual would be spikes up and down as we went through the pandemic. Is that a correct interpretation? And my second part, I mean, right now that we're in a pandemic situation, so there's a more urgent knowledge needed that could influence policy at present, and the post-pandemic situation, where I think your work will, really contribute. So my final question to you is, what is the most urgent next step for the work that you're pursuing? What should be done next? Thank you very much.
Yeah, so the first question about the immunology in terms of the spikes and whether it goes up and down, that's definitely something, yes, I agree, that's what's observed in those studies, and it does generally concern me. Most of the data that we used was either waning data, say, to SARS-CoV-1 or MERS, where there weren't reinfections, or for SARS-CoV-2, we used this Gabjartsen data set that, as Alex mentioned, is a really nice data set because it's just basically the whole population. It's based on Iceland, is it where they just did it for everybody. So it was very general for the whole spreading disease. But my point is that it was a relatively short duration data set, which means that probably doesn't have a lot of those multiple spikes. And then we used the phylogenetic imputation for the rest, which was based on the human coronavirus data, which again was longitudinal. So therefore it took into account the much more spaced out endemic transmission that is going on. So none of what, so I agree with all that you said. I'm not concerned about it with regard to this particular analysis. And I would say the next step that we're super excited about and working on very hard on right now is exactly what Michael Hawksberg just mentioned, which is let's try to see if we can say something about how long these vaccines are conferring immunity. Now, there's going to be a lot of assumptions involved in that. We can't avoid a ton of assumptions, many of them to do with this pandemic-endemic difference that we have to watch out for. Some of them involved in like sort of assuming natural infection is a proxy for what vaccination does. Maybe they're doing something very different to the T and B cells or something like that, and therefore there's a distinction there. But I think, certainly the prima facie result, I think we can apply one to the other and say, this is what we should expect. And one of the things that I think Alex and I have talked a lot about in writing this up is there's sort of this idea in the world that we have to do the empirical study, and until we get the empirical study, we can't say anything. And I just think that's the wrong approach. The right approach is to say, we can say things about this. Let's learn what we can learn. That gives us a point to put on a chart to say, we think it's this. Let's act in the light of that knowledge that we have, and then revise it as we get more empirical data, as we gather more data. And I think this is an example where we really don't want to be flying with our blinders on. We want to be knowing what we're headed for most likely headed for, and plan on that basis. And then we'll just have to change our tracks if it turns out something is different.
That's great. I want to see if Alex or Hayley have anything they want to add, including kind of future directions that they would like to take this work.
Yeah, just to follow up with what Jeff said, since you mentioned I work on fish, one thing that struck me in starting to work on these viruses was this strange parallel where when I talk about fish, nobody knows what I'm talking about. And when you talk to general audience about viruses pre-pandemic, nobody knew what you're talking about. We know very little about the biodiversity of these large groups. And I think that a lot of messaging that's been lost or a lot of mismessaging that's occurred is due to unfamiliarity and assuming that something that works in measles is going to apply to a coronavirus. And I think, by harnessing the power of evolutionary biology, the theme of this group, I think we really can say a fair bit and fill in the gaps of how we expect things to behave. And I think that's really useful for our future where zoonosis is going to occur again. So I just wanted to follow up with what Jeff was saying. I think that this we tend to think of evolutionary biology as this very historical thing, but I think it's so vital to human health. And I think this is a really cool application of it. It's been a blast to work on this with Jeff.
That's great, Alex. Hayley, do you want to add anything?
Yeah, and as we've kind of mentioned, this is an average over averages for the average Joe, but I think that the next step also would be to kind of look at people that have weaker immune systems and seeing what we can gather from that data and see if we can make any sort of estimates in that respect.
That leads into one of the questions I had. I was wondering what are, given that these HCOVs have been so well studied, I wonder what's known about the other factors that influence infection, such as nutrition, sleep, things like that. I'm aware of studies on sleep, for example, where they've, exposed people to rhinoviruses and see if, the amount of sleep that they had predicts whether or not they become infected. with rhinoviruses. And so I think an important component for those of us living in this pandemic is to also think about how we should be living. And then I think another component of that is, thinking about global health. We need to think about the effectiveness of these vaccines in low resource settings where maybe people don't have access to the same nutrition or calories or other factors like that that might influence the durability of immunity that they have. Is anything known about that with the circulating human coronaviruses?
I don't have an
Yes,
answer.
not.
So, but I will add one more since you mentioned that, and since we were just talking about future directions as well, and related to that, another future direction that we've already taken, and we have basically submitted work on right now, but it's not out yet either. Is we looked at globally what is the effect of seasonality on SARS-CoV-2. So basically the same kind of framework that I showed you here, we can apply to the human coronaviruses where data has been gathered already for different locations around the world for what their seasonality is, and impute from that what exactly the seasonality for SARS-CoV-2 might be. And that has a similar advantage to this in the sense that, like, there have been studies out there that have been widely panned trying to look at seasonality of SARS-CoV-2 because there's so many confounding factors. There's like, what did this nation do, and all the interventions that are going on, the fact that it's a pandemic, so stochastically, oh, there's a naive population, it spreads really fast. There's so many complexities that it's really hard to make any heads or tails out of the seasonality of SARS-CoV-2 right now. But we can figure out, sort of back out of that and just say, well, look, what would it be endemically? And then presumably it's some function of that, some scaling of the endemic seasonality is probably what we're actually seeing underlying the spread and emergence of SARS-CoV-2 now. And so, that's an exciting project that is a follow-up on this as well.
Yeah, that's a great direction. Great direction. Thanks for bringing that up. We're almost at the top of the hour. I'm going to try to fit in 2 more questions if we can. We'll see if we can do this. Barnett, would you like to ask your question?
Yes, I would. First, I'm a clinician. I'm a physician. I practice frontline. I've been there since the beginning of this, starting telemedicine in March 2020 with drive-through COVID testing, et cetera. So that's one thing I wanted to mention. I've been interested in evolutionary biology since medical school back in the 70s. I also want to apologize because I did share the link. That's why some of you might have noticed 2 names for me up there. Barnett Menon, a clinician friend of mine, Dr. Jerry Ehrlich. He was there too. I didn't realize the links shouldn't have been shared. It will not happen again, and I apologize. I just wanted to mention that when we test patients for antibodies, we do the spike protein via LabCorp and the nucleocapsid. And our understanding is the nucleocapsid positivity shows previous actual infection, where the spike protein is in response to the vaccine. My anecdotal experience in the last 3 months, I have seen 16 cases of positive COVIDs. All were more or less symptomatic. 15 of the 16 had been fully vaccinated, mostly with Pfizer, 1 J&J and 1 Moderna. And they were at least 2 months past fully vaxxed. Only one of those patients was very sick and required monoclonal antibodies. So interesting that he had an autoimmune disease. The other thing I wanted to say, the difference, again, anecdotally, take it for what it's worth. I work in Bethesda, Maryland, which is a very highly vaxxed population for many reasons. So that would tend to skew the patients that I see who are vaxxed and have breakthrough cases. 2 other observations. One is that compared to the first strain that came in a year and a half ago, we're seeing nasal congestion with the Delta. We did not see nasal congestion with the first strain. Secondly, the cases that I'm seeing on breakthrough are remarkably younger. 12 of the 16 were under the age of 50. So that was different than the first wave. And it would be wonderful to have a correlation between infection rate and the spike protein level. And I assume you're working on that. I think you intimated that, and that would be incredibly helpful for us clinicians. And with that, I will sign off. Thank you for listening.
Thanks for those observations and the suggestion and question. Jeff, did you have anything you wanted to say?
Well, just an answer to the last thing, which is that when this comes out, there will be, you know, this function that we've figured out, that we've calculated for the probability of infection given antibody level. Now, that has to be presented carefully. Like, we don't want to claim that this tells you how likely you are to get infected currently in the pandemic. Just like we were talking about with Kacha, like, it's really complicated for any individual in any circumstance in any place what your probability of infection is. But it does give you, I think, the right scaling of what your likely infection chances are given your antibody level. In other words, given your antibody level, like, how worried should we be about your chances of getting infected, you know, again, averaging over all other risks. And so that definitely is there. It's one of the plots that I showed in the talk today. So so I hope it's useful to people. And I also hope, though, that people are cognizant of what the strengths and weaknesses of that are as a measure. It's not meant to say what probability, you know, your probability of getting infected is. That's not really what it tells you.
Okay, thanks. We are going to squeeze in one more question. We're usually pretty careful about stopping at the top of the hour. But Ozgun Erdogan had a good question in the chat and has tuned in to ask the question. Please go ahead.
Thank you. This was a great talk. I really enjoyed it. Let me find my question. So all of your analysis is based on endemic conditions. So I was just thinking COVID-19 will eventually be an endemic, right? So if we assume that it's going to be an endemic, and if we assume that the mutation rate will not be too high as it is right now, at least eventually, what do you think about the potential studies that are focusing on pan-coronavirus vaccines? So based on your analysis, the reinfection time is different in each virus, in each strain that you studied. So I was wondering if it is worth investing in a pan-coronavirus vaccine versus just, you know, focus on separate strains. Thank you.
Maybe Alex, you want to take that first, and maybe I'll have something to say at the end.
Sure. Yeah. There's just sort of, for the vaccine development, one thing that is interesting is that there are regions across all these coronaviruses that seem to be under very strong purifying selection, that if we can find a way to make them presentable to our immune system, that they could provide potential targets. I don't develop vaccines, but I would imagine that if you could perhaps, you know, make something that targets that tiny bit of the envelope protein or something that is fairly conserved, that could present a viable target. But again, I would imagine that's incredibly difficult. But from comparison of the genomes, right, there are some regions that are fast evolving, some that are not. So it is, you know, likely, you know, it's potentially feasible to do something like this. And I would be hopeful that something like that is possible. An alternative approach might also be to think about these as clades and develop a few for specific clades of coronaviruses as well. So taking more of an evolutionary approach to say these, you know, SARS-CoV-1 and SARS-CoV-2/MERS seem to be more similar. Maybe we can make a pan vaccine for those. It's something I haven't heard anybody talk about, but something that I was, as you were asking your question, I was speaking about. So yeah, it's I think, you know, it's definitely a frontier for people to think about. I don't know, Jeff, if you have anything to add.
I do. Hayley, do you want to say something first, or should I just move on to what I'm going to say here?
You're welcome to go.
Okay, so I'm actually going to very quickly share my screen again for one of the slides that I showed you, just because it will help me narrate what I want to talk about a little bit, which is this doesn't really directly answer the question, but it's just my speculation in this area. And again, this is speculation. I'm not a vaccine manufacturer. There could be something wrong with the general ideas that I'm expressing. So it shouldn't be taken as gospel, but as creative thinking. Basically, I've been interested in this question a lot. Like, I was very curious when I heard that the vaccines were being generated, but before they mentioned what gene they were targeting, I was very curious about that. And it turned out they were targeting spike, and all the immunologists thought, oh, this is a fantastic target because you know what? That's what your immune system sees, and that's what the neutralizing antibodies were. And it's true, it's a great target in that sense. Like, it's a great target because the immune system does recognize it, and therefore you put a vaccine in someone's arm and they're going to be, they're going to be resistant to spike. Unfortunately, it's a terrible target in the other sense, in the evolutionary sense, that spike is exactly what that virus has evolved as an entity to cover its outside so that it can evolve to evade immunity, right? So spike is its camouflage, so to speak. And so why we'd want to design an antibody to the camouflage is a question that occurs to me a lot. And you can see that right here in this plot right here. So like, this is the phylogenetic informativeness over time, which correlates to how rapidly the genes evolve. So the faster they're evolving on this particular phylogenetic informativeness plot, the higher their informativeness and the faster, and so spike is this purple one here, it's evolving extremely quickly compared to the other genes. So, and again, this is all at a much slower rate than flu is evolving, but just relatively speaking, it's evolving at a fast rate. And that's because every variant that it produces tends to give it some evasion of immunity, apparently. Not every variant, but variants often give it some ability to evade immunity. Other genes in the genome do not have that same property of evolving quickly. Particularly, take a look at M, and which is actually a membrane gene, so it could in principle be targeted by an antibody. I don't know what the difficulties of that are. It is recessed from the spike tips, so it might be difficult to get an antibody in there, but it's a much slower evolving gene, and the E gene as well, very, very slowly evolving gene. So so I think it would be really advantageous if we could. It might be quite hard to design a vaccine that does it, but I think it would make a lot more sense to target M or E. It would give you much longer durability of immunity if you did, because those genes really do not evolve at nearly the rate that spike does. So that's my sort of speculative vaccine engineering thought in response to your question.
Okay, thanks, Jeff. Thank you for that great question, Ozgun, and everyone else who contributed questions. We're going to have to wrap up. We're past the hour. We usually try very hard to avoid that. So I'll just say thanks, Jeff. Thank you very much for presenting this work, and for also bringing along Alex and Hayley. Really great to hear your perspectives as well, and to meet you, Hayley, for the first time, and to see you after a long time, Alex, since you moved to Charlotte. Anyhow, thank you guys very much. Stay tuned for the next Club EvMeds. We've got a lineup that you can find on our website, and we're adding to it in the coming weeks with a few more talks. So hope to see you guys next time. Thanks again, Jeff, Alex, and Hayley.